Hello everyone and welcome to another short video on solving a LeetCode problem with APL. My name is Rodrigo and for the next couple of minutes we will be solving problem 1486, XOR operation in an array. Now the problem statement is very simple, it's very algorithmic. It tells us that we are going to get two integers as input, an n and a start. We need to define an array of numbers that's twice the indices plus the start, so the start is kind of an offset, and then we need to return the bitwise XOR of all of the elements in this array. Let's take as an example, let's take this n equals 4 and the start equals 3. So the original array, or the array that we start off with, is 3, 5, 7, 9, because that's going to be 0 plus start, 2 plus start, 4 plus start, and 3 plus start and 4 plus start, and then we do the bitwise XOR of everything, and there's an 8. Now, I've spent a couple of minutes trying to come up with a I don't want to say shortcut, but like a formula that figures out the result of the bitwise XOR, because the way we define the original set of numbers is it's a fixed formula, so I thought that maybe we could, I don't know, somehow maybe like distribute the bitwise XOR between the numbers and the additions and etc. But nothing obvious came to mind, so I didn't worry too much about it. But feel free to spend some time trying to come up with a more efficient solution. So let's say a closed formula for that. But so for our example, what was it? We had n equals 4 and the offset is equal to 3. And so the original numbers that we need to come up with is going to be the offset plus 2 times the iota of n. So these are our numbers. And now we need to do the bitwise XOR. Now in APL we don't have a bitwise XOR like in many other languages, which is generally this symbol right here. In APL what we need to do is we need to convert to binary explicitly and then use the not equals function to compare the bits and then convert to decimal again. So to convert to binary, what we do is we do this. So this was just me experimenting. I never know the order of things, so we can actually get rid of that. Okay, so with 2 decode power minus 1, we get the binary digits. Now we can do a reduction on each row with not equals reduce, and now we can convert this back to decimal. Now there's something really interesting here, and I'll take this opportunity to show it to you. If you take a look at this thing right here plus this one, these two are the inverse of each other. These two functions are the inverse of each other, and we only need them because we need to temporarily convert to binary so that we can do the not equals reduction and then we convert back to decimal. And this is this pattern of doing something as pre-processing and undoing it as post-processing is a very common pattern. And so sometimes we define something like this. We're going to define an operator that's called under, and let's see, it's going to be let me type it first and then I'll tell you what I'm doing. With this one, this one, this one. Okay, and the idea of this operator is that you type in your main function, so your main function goes here, and then you say that it's going to be under some pre-processing. For example, people do surgery. Gosh, I'm just realizing I can't spell surgery. Oh, it's something like this, surgery. So people do surgery under anesthesia. Anesthesia, I think this is correctly spelled. So what happens is the doctors give you some anesthesia, you fall asleep, the surgery happens, and then you wake up from anesthesia. So it's something that's done and undone. And here we have the same idea. So the only thing we want to do is we want to do a not equals reduction under conversion to binary. And conversion to binary is just this. Right? And this is after, and we do this after building the the expression that we want. So that's 2 times iota n. So our solution is really, this is the bulk of the work, and this just builds the sequence. So if we have a function, our solution function that takes the n, let's say that it takes the offset on the right and the offset on the left and the n on the right, then it's going to be the not equals reduction under conversion to binary, and then we do the alpha plus 2 times iota omega. And now our solution works like this. So offset the solution n gives 8, and the other examples we have here is offset is 0 and n is 5. So the offset is 0 and n is 5. This should give 8 as well. And finally, let's see, n equals 10 and offset is 5. So the offset is 5 and n equals 10. And we got a 2. Okay, so, and well, might as well just do the last one. So offset is 7 and n is 1, and so we get a 7. Okay, so this is it. I think this is the most obvious solution. I just showed you this interesting operator. Oh, I didn't go over this too much. So very quickly, in APL you define you can define operators with this syntax, and here notice that if omega is the right argument to a function, then omega omega is the right operand in the operator. So when under is called with this, what's happening is this is being seen as the right operand, so the function on the right. And so what we do is we take the input, which is omega, and then we do the binary conversion on that, which is this bit right here. Then alpha alpha is the function on the left, which is the reduction. So we apply the reduction. And then this thing right here, this is, again, the function on the right, but to the power of -1. So this is the inverse of that function. And so we invert this function, and then we get something that converts from binary to decimal, because this function converts from decimal to binary. And that's just how this works. And yeah, and there's all sorts of interesting things you can do with under. Of course, it doesn't work with all functions on the right, but this is something that may be added to APL sometime in the future, and when it's added, you will see that it pops up naturally in many places. You know, it might look like kind of weird, but it's actually a very natural thing to do. And yeah, I think that's it for now. If you have any questions, feel free to drop them in the comments below. Otherwise, I'll see you in the next video. Bye.